Okay, I'm going to try this one more time here. You don't know how many times I've tried to record this. I even tried to put a song in here for you guys, but it's not going. So we'll listen to the song and see the video in class, and I'll work on making sure these vids are working properly. So we're ready to start. Unit 5 for Ms. Howard's chemistry class, electrons in the periodic table. State of Texas says that C6B, you will understand the electromagnetic spectrum and the math relationships between energy, frequency, and wavelength of light. C6C, you will calculate the wavelength, frequency, and energy of light using Planck's constant. And you'll express the arrangement of electrons in atoms through electron configurations and Lewis valence dot structures. There is more. Yes, there are more teaks here, but we'll talk about those in the next couple of PowerPoints. So we start off on your notes, Roman numeral number 1. You'll notice that there's a place here that says Eureka video. Yes, I tried to put that on, and it took me, I spent 45 minutes trying to put it on, and it just kept crashing, so I'll see it in class. Roman numeral number 1, light. Why are we talking about light when we're talking about electrons? Well, there's a reason for that, so bear with me. Light acts as both a particle and a wave. And it's actually a form of energy. So when we talk about it acting like a particle, we're talking about it acting like matter. And when we talk about acting like a wave, we're talking about it acting like energy. So matter and energy are not the same thing. Okay? The universe is made of either matter. Everything in the universe is made of either matter or energy, one of the two. Okay? Now, the electromagnetic spectrum, usually when we talk about energy being given off by the sun, we humans are kind of focused on light because that's the part we can see. But there's a lot more given off by the sun than just the energy that we can see that we call light. So, and you guys know this stuff. The electromagnetic spectrum includes all of these waves. Radio waves, you know about radio waves. We can even create our own. We don't have to get them just from the sun. Microwaves, infrared. Infra means below, so it's below red. Visible light, red, orange, yellow, green, blue, indigo, and violet. Ultraviolet, ultra means above, so it's above the violet. X-rays and gamma rays. So you guys are familiar with most of these. What's key here is that when you talk about the radio waves, they're low frequency. That means a lot of waves don't pass a point in 1 second, and they have a long wavelength. And as you go down this list, the frequency gets higher and higher, and you get shorter and shorter wavelengths, and you get greater and greater energy. Radio waves zip through your body all the time with no problem. You can't say quite so much the same thing when you talk about X-rays. That's why people who are X-ray technicians, they don't stay in the same room with you whenever they're doing X-rays. They do those X-rays all day long. They stand behind a kind of a partial wall or even in a different room to protect their bodies from the X-rays. It's also the same reason they would tell you, don't get a lot of X-rays in 1 year. 2 or 3 X-rays in a year is enough because those X-rays can actually damage the tissue. And then, of course, you have gamma rays. Don't mess with those. Here we have a picture, and off to the left you have radio waves, off to the right you have gamma rays. And if you look, the radio waves, they're kind of spread out, it seems like. So you have long wavelengths and low frequency. And then as you go off to the right, the waves are closer and closer together. So you have shorter wavelengths and higher frequency. A lot more waves pass a point in 1 second. And then you see that little dashed line kind of towards the right that says visible light. Out of all the stuff, the energy given off by the sun, we only are able to see a tiny little piece of it, and that's it. So here's one more representation, and in this case you've got them flipped, so the gamma rays are on the left and radio waves are on the right. But again, you see how all of that stuff is given off by the sun, and we only see a little bitty tiny bit of it. Yes, there are radio waves given off by the sun. By stars. Stars give off radio waves. They have telescopes that can sense radio waves, so we can get all sorts of information. Now, if you look at the top wave, the little red one, across the top of the picture it says it's 1 second. So in that top red wave, you get 4 waves passing a point in 1 second. Now, how do you know how much is a wave? You see that little upside down looking Y thing? That's a lambda, and that's what they use to represent a wavelength. So we can go from a point on one wave to a point on the next, and that's one wavelength. In this case, they went from the top of one wave to the top of the next, and you get one wavelength. You go to the middle one, and you notice that the wavelength is shorter because you have more waves passing a point. You have 8 waves passing a point in 1 second. And then you go to that bottom one down there, and they're really a lot shorter, and you've got 16 waves passing a point in 1 second. A lot more energy there. Long wavelengths are low frequency, low energy. Shorter wavelengths are higher frequency and higher energy. And the shorter that wavelength, the higher the frequency, the more damage it can do to a human. Some damage is not quite so bad as others, obviously. Like if you go outside in the sun during the summer, you might get a sunburn. That's damage from UV rays. Ultraviolet. Now, in between the last slide and this one, there was a lovely song for you guys with a video, but we'll see that in class. Number 2, we can calculate, yes, we can calculate the velocity of a light wave. Velocity, V, equals frequency times the wavelength. But we're not just talking about any wave, we're talking about light waves. So somebody already figured out the speed of light. That's 3 times 10 to the 8th meters per second. So it'll go 300 million meters in 1 second. Somebody already figured that out. So instead of just saying generic velocity, we can stick this letter C in there. That's the speed of light. So 3.8 times 10 to the meters per second is equal to the frequency times the wavelength. I know you're so happy with those numbers. We can also calculate the amount of energy the wave has. So energy is equal to this hf, where f is the frequency, again, just like in the last one, and h is this weird thing called Planck's constant, which is an ugly number, and capital E, again, is energy. So energy in science is typically measured in joules. You know, we can also measure energy in calories, but mostly in science we use the metric system, so we measure things in joules. Planck's constant is 6.62 times 10 to the negative 34 joule seconds. And then we have frequency, and frequency is usually measured in hertz, which is cycles per second, or how many waves pass a point in 1 second. All right, number 4 on your notes, a photon. A photon, and if you're a science fiction fan like I am, every time I hear the word or see the word photon, I think, oh, photon torpedoes. But some of you guys fear those things called books, so you don't read much of that. But anyway, a photon is like a piece or a little packet, a little quantity of light, and they call it a quantum. We usually only, again, think about visible light, but remember, all the energy given off by the sun, we can say we could talk about them in the terms of photons. So the part we can see would be the colors of the rainbow. Roy, G, Biv, red, orange, yellow. G, green. Biv, blue, indigo, violet. Now, why are we talking about light? Because electrons act in the same way as photons. They also act as both particles and waves. So whatever calculations we can do with light, we can also do with electrons. Oh, joy of joys, right? So number 1 on your notes, they are the only parts that are small enough to be affected by a photon. Do you remember we talked about the mass of the atom, the atomic mass or the mass number? And they just got that by adding protons and neutrons, and they ignored the electron because it was so tiny. Well, here, it's the only thing that's tiny enough to actually be moved by a photon. So a photon comes down and smacks that electron. It'll cause it to vibrate so it can get it to move, which makes amazing things happen. Now, you remember a man by the name of J.J. Thomson who discovered the electron. He said that that electron acts like a particle. Well, his son also won a Nobel Prize, but he won the Nobel Prize for saying, you know, it acts like a wave. The electron acts like a wave. Yeah? Well, then along comes another guy and says, gentlemen, and he really needs a new hairdo. But he said that you actually have both. Both of you guys are right. The electrons act as both particles and a wave. So in order to understand the electrons, you have to understand the electromagnetic spectrum, or light. The end for the moment.